Let's start by reminding ourselves of the difference between scalars and vectors. A vector is a quantity that involves both a size or a magnitude and a direction. So some examples of vectors are displacement, velocity, acceleration, force, and so on. Scalar quantities don't involve a direction, so they have just a magnitude. So examples of scalars would be time, mass, temperature, and energy. The simplest vector quantity is probably displacement. When we studied displacement earlier, we focused on one-dimensional motion, or motion in a straight line. The reason that motion in a straight line is called one-dimensional is because it only requires one single coordinate axis. We start by taking an arbitrary point to use as our origin. In this example, we'll take the tree as the origin and we will assign it a coordinate of 0. We can then measure distances using positive coordinates in one direction and negative coordinates in the opposite direction. We can represent the displacement of a moving object by drawing an arrow starting from the object's initial position, ending at the object's final position. The length of that arrow is called the magnitude of the displacement vector. We can calculate the displacement by subtracting the final position minus the initial position. In this example, the bicycle starts with an initial position of -6 meters and ends with a final position of +4 meters. So if we subtract those two positions, we get +10 meters for the displacement. The 10 meters, that's the magnitude, that's the length of the arrow. The positive sign tells us which direction the bicycle is moving in. For 1D motion, there's only two possible directions. You can either move in the positive direction or the negative direction. Now let's look at some motion that's not in a straight line. This green rectangle, think of that as a soccer field. A player on the soccer field is now moving in two-dimensional motion. We call it two-dimensional motion because to describe the player's position requires two coordinate axes. In the illustration, we've chosen the center of the field as the origin. We've drawn the x-axis along the center of the field from one goal to the other, with positive values for one team's side of the field and negative values for the other team's side of the field. The y-axis goes across the field with negative numbers close to one sideline and positive numbers close to the other sideline. Now, if we record the player's position based on where she's standing on the ground, she's got an x-coordinate of -10 meters and a y-coordinate of +5 meters. That ordered pair, the -10 and the +5, represent her initial position. If she were to move to a different position, we would illustrate her displacement just like we do in 1D. We would draw an arrow starting at her initial position, ending at her final position. The length of the arrow, just like in 1D, is called the magnitude of the displacement vector. To describe the direction of the displacement is a little more complicated. Remember that in 1D there's only two possible directions, positive and negative. For two-dimensional motion, there are basically infinitely many directions that the person could run. So scientists and mathematicians have decided to use the direction parallel to the positive axis. We're going to call that 0 degrees. So if a player was, say, here and ran in this direction, we would call that direction 0 degrees. Any other direction can be described by an angle measured counterclockwise from 0 degrees. So on this illustration, the red arrow represents our soccer player's displacement. If we got a protractor and measured the angle between the blue and red arrows, it's going to be about 37 degrees. So we would say that our soccer player has a displacement with a direction of +37 degrees. If the soccer player had run in this direction, directly towards the sidelines, we would describe her direction as +90 degrees. 180 degrees would mean back towards the goal at the left side of the field. If she were to run towards the other sideline, we'd describe that direction as 270 degrees. Suppose a displacement had a direction of +315 degrees as illustrated. What that 315 degrees means is if we were to measure the angle from this blue 0 degree arrow all the way around the outside, that would be 315 degrees. It's often more convenient to measure this smaller angle in the clockwise direction. So to indicate that we've measured a direction clockwise rather than counterclockwise, we would describe the angle using a negative number. 315 degrees counterclockwise is effectively the same as 45 degrees in the clockwise direction. So negative 45 degrees and positive 315 degrees are in fact two ways of describing the exact same direction. We can convert between positive and negative angles simply by adding or subtracting 360 degrees. If we were given a direction of negative 45 degrees and we wanted to express that as a positive angle, we would simply add 360 to the negative 45 and we would get positive 315 degrees as the direction. Now, in order to do any math with the direction needs to be expressed as an angle, which is a number. Sometimes you'll be given directions as compass directions, like north, south, west, or east. Most of the time, we take the x-axis to run from west to east, and we take the y-axis to run from south to north. Now, remember that the origin and the directions of the axes, those are totally arbitrary. So this isn't always going to be true, but that's the most common way of converting compass directions to angles. Now, often a direction won't be exactly north or exactly east, so you may see a direction described with two directions and an angle. So suppose I told you a vector, say a displacement, had a direction north, 10 degrees east. What that means is, of the four compass directions, it's closest to north, but it's 10 degrees towards the east. So if we wanted to convert that or to express that as an angle, we know that north is 90 degrees, so turning 10 degrees to the east would give us 90 minus 10. We would describe that direction as positive 80 degrees. If a direction is described, for example, as southwest with no angle, that means exactly halfway between south and west, or 45 degrees. So since west is 180 and south is 270, southwest is halfway between. You can calculate that two ways. You could go 180 plus 45, or you could go 270 minus 45. Both would give you 225 as the direction.